For the second topic in Unit 2, we're going to have a look at rational expressions. Rational expressions will feature polynomials in fraction form. So you'll see here in this first example, our directions say find all x values for which the expression is undefined. And we have this rational expression. We have a polynomial on the top and a polynomial on the bottom of a fraction. We want to find all x values for which this rational expression is undefined. Now, the expression is only going to be undefined when we have a denominator equal to 0. So you know that you cannot have a 0 on the bottom of a fraction because you cannot divide by 0. That is something that is undefined. So when this rational expression will be undefined is when this denominator, when the bottom of the fraction is equal to 0. So what we can do is we can take the polynomial, which happens to be a quadratic, and we can set it equal to 0. From here, we want to find the values of x that create this equality. Okay, we want to find what values of x yield 0 on this side of the equal sign. So we can use the knowledge that we gained in Topic 1 from Unit 2 to continue from here. So I'll have a look at this quadratic, and it doesn't look like there is any common factor between these three terms, so I can't pull anything out at first, so I will go ahead and ask myself, what are two numbers that multiply to, let's see, 1 times negative 28, multiply to negative 28, and add to negative 3. So two numbers multiply to negative 28 and add to negative 3. How about 7 and 4? 7 times 4 is 28. I can make either one negative to make the 28 negative, but I need that 3 to be negative. So when I add them together, I need to get a negative 3. I better put the negative on the 7. So negative 7 times 4 is negative 28, and negative 7 plus 4 is negative 3. That will work. I will now replace this negative 3x with my two numbers. So I will replace that with 4x minus 7x, and I've just rewritten my x squared and my 28 and my equals 0. Now I have 4 terms that I can factor by grouping. For the first group, my common factor is x. I'll pull out an x. I'm left with an x plus 4. For my second group, I have a common factor of negative 7. If I pull out this negative 7 and divide each term by it, I'm left with x plus 4 on the inside of the parentheses. Okay, I carry down my equals 0. Here I have a common factor among the two terms. The common factor is x plus 4. So when I pull out this x plus 4, I'm left with x minus 7 in my other set of parentheses. Now I have two factors multiplied together, and I know these two things, when multiplied, equal 0. That means either x plus 4 equals 0, or x minus 7 equals 0, or both. This leads me to my solution, x equals negative 4, and or x equals 7. So anytime you are asked to find values for which a rational expression is undefined, you will take the bottom of that fraction and set it equal to 0, and then solve for those values. You might also be asked to simplify a rational expression. This is our second example. We can simplify 3x minus 12 over 5x minus 20. In order to simplify, we're going to factor the top and factor the bottom and see if anything cancels out. So in the top of my fraction, this polynomial, I do have a common factor of 3. If I pull out that 3, I'm left with x minus 4, and I can do the same thing to the bottom. 5x minus 20, that has a common factor of 5. I can pull out the 5, and I'm also left with x minus 4. Now you'll see this new version of our rational expression has a common factor on the top and the bottom. This x minus 4 will divide out with this x minus 4, leaving just 1. So we have just the 3/5 left over. Our simplified version of this rational expression is just 3/5. Let's try another one. This one has a quadratic on the top and a quadratic difference of squares on the bottom. I'm going to factor the top and factor the bottom. So for the top, let's see, I want to find two numbers that multiply to negative 15 and add to 2. How about 5 and negative 3? 5 times negative 3 is negative 15, and 5 plus negative 3 is 2. That will work. So I will rewrite this rational expression, and I'm going to replace the top with a new version of itself. I'm going to replace the 2x in the top with a 5x and a negative 3x. I've written that out here. So I've taken this 2x, replaced it with negative 3x plus 5x, which really is the same thing. Next, I'm going to factor this top quadratic by grouping now that I have my 4 terms. So I'm going to look at the first group, x squared minus 3x. That has a common factor of x. When I pull out that x, I'm left with x minus 3 from these first 2 terms. For the second group, 5x minus 15, I have a common factor of 5. If I pull out the 5, I'm left with an x minus 3. Okay, for our next step here, I notice now I have an x minus 3 and an x minus 3. That is a common factor among these 2 terms. I'm going to pull out the x minus 3 and I'm left with x plus 5. It looks like I'm done factoring the top of my fraction, so let's move on and factor the bottom of the fraction. X squared minus 9. If you recognize this as a difference of 2 squares, you can go right ahead and jump right to the next step of x plus 3, x minus 3. If not, that's okay. We're going to find 2 numbers that multiply to negative 9 and add to 0. Well, if they're going to add to 0, they have to be the same number, one positive and one negative. So the square root of 9 is 3. Let's try 3 and negative 3. Okay, I could rewrite this if I like as x squared plus 3x minus 9 and factor by grouping. If you proceed to factor by grouping, you might want to write this out in your notes. You'll see that your result is x plus 3 and x minus 3 as your factors for the bottom of the fraction. Now I'm going to look at this rational expression as a whole. I've factored the top and factored the bottom, so I'm going to look for common factors among the top and the bottom. It looks like I have an x minus 3 in both places. This x minus 3 and this x minus 3 will cancel out to equal 1, and I'm left with x plus 5 over x plus 3. That is the simplified version of my rational expression. Next, we're going to have a look at some operations that we can do with rational expressions. On this page, we're going to look at products and quotients of rational expressions. So in this first example, I have a product of rational expressions. I have this rational expression multiplied by this rational expression. When you're multiplying rational expressions, it's actually quite straightforward. You simply multiply across the top and multiply across the bottom. So I'm going to take this x squared plus x minus 20 and multiply that whole thing by 7. Just for neatness sake, I've put the 7 out front here, but you can see that the tops are just multiplied together. And then I'm going to do the same thing with the bottom. I'm going to take 21 and multiply it by this whole polynomial 3x squared minus 11x minus 4. So I have this multiplication, it's written all together, and it looks like I have 2 of these quadratics here. Neither one has a common factor within the expression, right? X squared plus x minus 20, no common factor in itself there. Same thing with this quadratic here, 3x squared minus 11x minus 4. 3, 11, and 4 don't have any common factors either. Okay, 7 and 21 do have common factors here in the whole expression. If you'd like to simplify this at this step, you can, but in my writing here, I do it at the end. Either way will work the same. So my quadratic on the top and quadratic on the bottom, I'm going to factor those. I'll do them both at the same time just to save some space. So for the first quadratic, I'm looking for 2 numbers that multiply to negative 20 and add to positive 1. Let's see what will work there. How about 5 and 4? 5 times 4 is 20. If I make the 4 negative, I will get a negative 20, and that also gives me a 1 when I add 5 and negative 4. So I'll replace this positive x here with a plus 5x minus 4x. Everything else on the top of the fraction stays the same as is written above. Let's do the same thing with the bottom quadratic. I'm looking for, let's see, 3 times negative 4 is negative 12. Two numbers, so you have to multiply to negative 12 and add to negative 11. I've written that out here. How about 12 and 1? 12 times 1 is 12, and if I want it to be a negative 11 when I add them, I better make that 12 negative. Negative 12 times 1 is negative 12. Negative 12 plus 1 is negative 11. So I'll replace this negative 11x with a negative 12x plus x. Everything else on the bottom here is the same as what is written above. Now I have two quadratics that are featuring 4 terms, so I can factor by grouping for each one. Let's start with the top. My first 2 terms in the group, the first group, x squared plus 5x, I can pull out the common factor of x and I'm left with x plus 5. In my second group, negative 4x minus 20, I have a common factor of negative 4. If I pull out the negative 4, I'm left with x plus 5. Okay, I'm going to carry down this 7 in the large parentheses outside as well. How about for the bottom quadratic? The first group, 3x squared minus 12x, has a common factor of 3x. If I pull out the 3x, I'm left with x plus 4. And here, x minus 4, I can pull out just a positive 1, and I'm left with x minus 4. So here, let's see, in my next step, I'm going to look at, again, these individually, these quadratics, top and bottom. Let's start with the top one. Here I will pull out my common factor of x plus 5. X plus 5 is appearing in both terms, so I can pull it out, and I'm left with x minus 4. For the bottom, I have an x minus 4 on both sides, so I can pull that out, and I'm left with 3x plus 1. Okay, I still have my 7 and my 21 on the outside. At this point, everything on top is just multiplied by everything else. Everything on the bottom is multiplied by everything else. So we are safe to cancel anything that we see. 7 and 21, 7 divides into 21 3 times, so I can cancel this out as 1 over 3. X plus 5, there's no other x plus 5s here, but x minus 4, here's an x minus 4. These x minus 4s will cancel on the top and bottom, cancel to 1. So I'm left with x plus 5 from the top, and the 3 from the 21, and the 3x plus 1 on the bottom. So this is the product of these two rational expressions. We can also take a quotient of rational expressions or divide a rational expression by another rational expression. So in this second example here, I have a first rational expression with polynomials on the top and bottom, and a second rational expression the same, and I'm going to divide them. So I'm going to take this one divided by this one. Now, when we divide anything with fractions, you're going to multiply by the reciprocal. So division is the same thing as multiplying by the reciprocal. So I'm going to keep this first rational expression the same. You'll see I've rewritten it here the same. I'm going to multiply now instead of divide, change the division to multiplication. And I'm going to take the reciprocal of the second rational expression. The reciprocal is just the flip, okay? So you take the bottom of the fraction and move it up top, take the top of the fraction, move it on the bottom. So I've rewritten the second fraction here with the bottom on the top and the top on the bottom. When I was in school, they called this the keep, change, flip method. So you would keep the first fraction, change the sign to multiplication, and then flip the second fraction. Keep, change, flip, KCF, it's kind of close to KFC, can be easy to remember, but that is what you do when you are dividing any kind of fractions, in this case a rational expression. Once you've written your division in this form, well, now it's just multiplication, and it works the same way as the multiplication we did in the first example. So I'm going to multiply the tops and multiply the bottoms. So here in my next step, I've written the tops multiplied together and the bottoms multiplied together. Now remember, back to Unit 1, when you're multiplying polynomials, you have to multiply every term by every other term, okay? So that would be one way to do this. But before we go ahead and multiply a whole bunch of terms and then try to refactor, well, our ultimate goal is to simplify all of this. So why would I make it less simplified by multiplying across when I could make it more simplified by factoring? So I'm going to go ahead and factor. I'm going to take this first quadratic. I'm going to think of a pair of numbers that multiplies to 2 and adds to 3. That pair of numbers is 2 and 1. Okay, so I've written that here. And when I factor this, if you need to write down a few more steps here, that's fine. You'll see that the factors are x plus 2 and x plus 1. I'm going to do the same thing here with this quadratic. I'm looking for two numbers that multiply to 24 and add to 10. 6 and 4 will do the trick. So I will factor that here, x plus 6 and x plus 4. On the bottom, this quadratic, numbers that multiply to 4 and add to 5. How about 4 and 1? X plus 4 and x plus 1. And for this final quadratic, two numbers that multiply to 6 and add to 5. 2 and 3 will work. I have x plus 2 and x plus 3. Okay, so now I have 4 factors multiplied across the top, 4 factors multiplied across the bottom. I'm free to cancel out anything that's a common factor or appears the same on the top and the bottom. So x plus 2, I have an x plus 2 on the bottom. Those will cancel. X plus 1 will cancel with x plus 1. X plus 6 won't cancel with anything here, but x plus 4 will cancel with this x plus 4. So I'm left with the x plus 6 on the top and the x plus 3 on the bottom. This is the result of this very complicated looking division of rational expressions. Now that we've seen how to multiply and divide rational expressions, we're going to have a look at two more operations, and that is adding and subtracting rational expressions. So our first example here, we have one rational expression and we're subtracting from it another rational expression. Now, when we're adding or subtracting rational expressions, it follows the same rules as adding or subtracting fractions. If you need to refresh some of those ideas, it would be wise to do so at this point. So you can only subtract or add fractions if the fractions have the same denominator or the same exact bottom of the fraction. We need to express these rational expressions in such a way that the bottom of each of them is exactly the same. To do this, we're going to look for a lowest common denominator. Okay, the lowest common denominator is something that we can achieve using the parts of the denominators that we have multiplied by some other factor. Okay, the lowest common denominator in this case would use both of the factors that we find on each of our denominators. So it would be x plus 4 and x plus 6. If we have these two multiplied together, if we can change each of these rational expressions to have this as the denominator, then we will be free to subtract the tops of our fractions. Okay, so how do we get this x plus 4 to look like x plus 4, x plus 6? Well, we have to multiply x plus 4 by x plus 6. Now, in order to do that without changing the value of this rational expression, we have to multiply the top as well. If we multiply the top and bottom of the fraction by the same thing, we're not changing the fraction. So what I've written here is my x plus 2 over x plus 4, I've just copied that here, and I'm multiplying the top and the bottom by x plus 6. This results in a new rational expression that has my lowest common denominator on the bottom. I'm going to do the same thing with my second rational expression. I want this x plus 6 to be x plus 4 times x plus 6. So I need to multiply x plus 6 by x plus 4. If I'm going to multiply the bottom, I need to multiply the top as well. So I've rewritten this rational expression, and I'm multiplying the top and bottom by x plus 4. Now, in this form, you can see that the bottom of the rational expressions is the same. Now that we've achieved the common denominator, we can keep this denominator and then perform our subtraction on the numerator. So I'll take x plus 2, x plus 6, and I'll subtract from it x minus 1, x plus 4, and the denominator will be just this denominator, okay? So I've written that here. I have subtraction going on the top, and my common denominator is on the bottom. Now moving forward, you'll want to be careful, okay? You might think to yourself, oh, I have, x plus 6 on the top and bottom and x plus 4 on the top and bottom. Maybe I can just cancel those and they'll go away. Well, you can't, okay? You cannot cancel things at this point because we have this big old subtraction sign in the middle. And you cannot cancel from one side of subtraction or the other because whatever you would be canceling up here is not being multiplied by the entire numerator. It would only be it's attached to this guy. So it violates order of operations to do any canceling at this point, and that would result in an incorrect answer. So be careful that you're not tempted to cancel at this point. What I want to do is I actually want to perform this subtraction. Now, let's see, I can't really perform this subtraction very easily with these polynomials in their factored form. So what I'm going to do is I'm going to unfactor them. I'm going to multiply across so that I have my quadratic here and my quadratic here. So I'm going to multiply every term by every other term. X times x is x squared, x times 6 is 6x, and 2 times x is 2x, 2 times 6 is 12. I'll do the same thing with the other one. X times x is x squared, x times 4, 4x, and negative 1 times x, negative x, negative 1 times 4 is negative 4. So I've rewritten those top expressions as their original quadratics, and I've kept this minus sign in my parentheses. At this point, I can distribute this minus sign to every term in my second quadratic here. And once I've done that, I can consider this as well, an addition problem. Just a string of pluses and minuses on the top and bottom. But before I do that, I want to clean up a few things that I see in these quadratics. I have 4 terms in my quadratics here and here. I'd prefer to only have 3 terms. Let's combine these like terms, the 6x plus 2x into 8x, and the 4x minus x into 3x. This is a little bit nicer looking and easier to deal with. It's one less term on each piece to be bothered with. Now that this looks a little nicer, I will distribute this negative to each of these 3 terms. So I have negative x squared, negative 3x, and the negative 4 becomes positive 4. Now I can let my parentheses go, okay, because they were here to indicate that I was subtracting this whole thing from this whole thing. But now that I've distributed that negative, I just have this nice string of addition and subtraction going on in the numerator. Now I have many like terms that I can combine. X squared minus x squared, well, that will just go away. That equals 0. 8x minus 3x, that is 5x. And 12 plus 4 is 16. So my numerator, the top of my fraction, has become just 5x plus 16. Now there's no common factor between 5x and 16, so that is as simplified as we're going to get the top of the fraction. And the bottom of the fraction is already factored, x plus 4, x plus 6. There's nothing else we can do with this, so it must be in its simplest form. This is our solution to subtracting these rational expressions. Let's have a look at an example where we add some rational expressions like this one, 5x over x minus 3 plus 2 over 3 minus x. Once again, I need to create a common denominator, so I'm going to look for the lowest common denominator or the least common denominator. And x minus 3 and 3 minus x, those are very similar things going on, very similar. In fact, if I were to multiply this one by -1, this would be -3 plus x, which is essentially the same as this one. -3 plus x is the same as x minus 3. So my lowest common denominator, I will make it x minus 3, and in order to make this second rational expression match, I will multiply the top and bottom by -1. So that's what I've written here. I've just carried down the first rational expression, carried down the second, and I multiply the top and bottom by -1. Now you'll see I have 5x over x minus 3 plus -2 over -3 plus x, which is a fancy way of saying x minus 3. Okay, so I have the same denominator. That means I can just add across the top. 5x plus -2 is the same as 5x minus 2. And my common denominator goes on the bottom, x minus 3. There's nothing else here that can be factored out or canceled, so we are done with our addition of these rational expressions. There is one final type of problem that you will be asked to solve regarding rational expressions, and that is solving rational equations. So up until now, we've dealt with expressions that don't have an equal sign in them to begin with. These are rational equations that do have an equal sign. So this page of notes will tell you how to solve for x or solve for y, any variable that might be in the equation. You can solve for that variable even when there is a fraction present. So the first thing I want to do, looking at this first example, x plus 12 over x is equal to 7. The very first thing you want to do before you start solving a rational equation is you want to identify values of the variable that would make the equation undefined. Okay, so undefined values of x, that would be any value that makes the denominator of the fraction 0. So in this case, the only thing I have on the bottom of a fraction is a lone x, okay? So if this x were to be 0, this equation would be undefined. So I will make a note, I will write this down, that x cannot be equal to 0. If it is, this equation is undefined. So that's the first step. The next thing we want to do is to try to solve for this x. In order to do that, I need to get x by itself on one side of the equation. So it would be best if I could get that x out of the denominator. One way I can do that is by multiplying both sides of the equation by x. As long as I multiply the left side of the equation and the right side of the equation by the exact same thing, I'm not actually changing the equation. So what I've written here is x times the left side of the equation, and what I've written here is x times the right side of the equation. I can go ahead and multiply these polynomials here. X times x is x squared, and x times 12 over x cancels out the x's and I'm left with 12. And on the right hand side I have x times 7, or just 7x. From here I can solve to get a 0 on the right hand side and to get my quadratic in standard form on the left hand side. So I've subtracted 7x from both sides, resulting in x squared minus 7x plus 12 equals 0. From here, I can use my knowledge of factoring to continue to solve for x. I'm going to look for two numbers that multiply to 12 and add to -7. -3 and -4 should do just that. -3 times -4, then negatives cancel, giving me positive 12. -3 plus -4 is -7. So I'm going to rewrite this equation here, carrying everything down, except I'm going to replace the -7x with -3x minus 4x. Here is my new polynomial with 4 terms. I'm going to factor by grouping. The first two terms have a common factor of x. When I pull out the x, I'm left with x minus 3. For the second group, -4x plus 12 has a common factor of -4. When I pull out the -4, I'm left with x minus 3. Okay, carry down my equals 0, and notice that I have a common factor of x minus 3. I can pull out those x minus 3's, and I'm left with x minus 4. X minus 3 times x minus 4 is 0. Two things multiplied together is 0, meaning that either x minus 3 is 0 or x minus 4 is 0 or both. Solving for x here, add 3 to both sides, I find that x is 3. And over here, adding 4 to both sides to solve for x, I find that x is 4. X is allowed to be 3 because the only thing x can't be was 0. And x is allowed to be 4 because, once again, the only thing x can't be is 0. So these values of x make up my solution to this rational equation. Let's have a look at another one here. 5 over y squared minus 9 is equal to 3 over y plus 3 minus 2 over y minus 3. So one of the first things that I want to do here is make sure I know all of the values of y for which this equation will be undefined. For sure, if y is negative 3, 3 minus 3 is 0, that would make the bottom of this fraction 0. And if y were positive 3, 3 minus 3 would make the bottom of this fraction 0. So 3 and negative 3 aren't going to work. They will make this rational equation undefined. Similarly, if I plug 3 in here, 3 squared is 9 minus 9, that's 0, so still no good. And negative 3 squared is also positive 9 minus 9 is 0. So it looks like 3 and negative 3 are all of the values for which this equation are undefined. Equation is undefined. So we'll want to make a note of those values. Next, let's go ahead and let's factor this quadratic here, because to solve this for y, we will need this factored eventually anyway. So y squared minus 9, that's a difference of squares, or you can factor this with our normal method by grouping. You'll find that you factor to y plus 3 and y minus 3 as your factored result. So I've rewritten everything here, replacing my quadratic with its factored form. Next, to get these variables out of the denominators, I'm going to multiply across the entire equation, the left and the right hand side, multiplying every term. So to get y plus 3, y minus 3 out of the denominator, I'm going to multiply by exactly that, y plus 3, y minus 3. In order not to change the meaning of the equation, I have to multiply both sides of the equation by this. So that means I have to multiply each term on the other side by the same thing. So I've multiplied this term by y plus 3, y minus 3, and this term by y plus 3, y minus 3 as well. So now let's go ahead. When I multiply this by this, okay, I have now y plus 3 on the bottom and the top, they will cancel. Y minus 3 on the bottom and the top, they will cancel, leaving me with a nice friendly looking number 5. Here in this next term, 3 over y plus 3, the y plus 3 will cancel with the y plus 3, leaving just the 3 and the y minus 3 in our first term on the right side of the equal sign. And for this term here, negative 2 over y minus 3, this y minus 3 will cancel with this y minus 3, leaving just the negative 2 and the y plus 3. I've written that here. Now I'm going to go ahead and I'm going to distribute this 3 and this negative 2. So that gives me 3y minus 9 when I multiply the 3 by each term, and negative 2y minus 6 when I multiply this negative 2 by each term. Now I have a nice string of things added and subtracted together on either side of the equal sign. I'm going to use some basic algebra to solve for y. So I can combine like terms. 3y minus 2y is just y. Negative 9 minus 6 is negative 15. To solve for y, I will add 15 to both sides, and 5 plus 15 is 20, and I've found that y equals 20. And 20 is okay because 20 is not one of the numbers that we decided y couldn't be, the numbers that would make our equation undefined. So our solution to this rational equation is y equals 20.